In the present lecture, we shall discuss the Cramer Rao lower bound of the variance of an unbiased estimator. This is abbreviated as CRLB. First, we shall discuss the regularity conditions under which one can define the CRLB. Next, we shall prove the main theorem along with the case of equality where the variance of an unbiased estimator attains the Cramer Rao lower bound. Some examples will be discussed in this connection. Finally, we shall provide two important results. The first result is related to the exponential family of distributions, and the second result is related to the lower bound of the mean squared error of a biased estimator. In this lecture, we consider a very important inequality which provides a lower bound for the variance of an unbiased estimator. Let the vector x, which is equals to x1, x2 up to xn, be a random sample from a population with PMF or PDF small f theta, where theta belongs to script theta. Let capital T be an unbiased estimator of an estimable parametric function g theta. We will consider the case where f theta is a probability density function. The development for discrete density functions is analogous. Suppose script f theta be the family of joint PDFs of the vector x. It satisfies the Cramer Rao regularity conditions which are given below. Number 1, script theta is an open subinterval of the real line. Number 2, the support script x, which is equals to set of all x vector for which f theta x greater than 0 does not depend on theta. Number 3, del by del theta log f theta x exists for all x and for all theta. Number 4, for any statistic hx with expectation of hx is finite for all theta, the operations of integration and differentiation with respect to theta can be interchanged in expectation hx. That is, del by del theta expectation of hx is equals to del by del theta integral hx f theta x dx, which is equals to hx del by del theta f theta x dx for all theta. Number 5, the Fisher's information I theta, which is equals to expectation del by del theta log f theta x whole square, exists and is positive for all theta. Now we are going to the main theorem. Let script f theta satisfies the above regularity conditions and capital T be an unbiased estimator of an estimable parametric function g theta such that g prime theta, which is equals to d by d theta g theta, exists for all theta. If variance of t is finite, then variance of t is greater than equals to g prime theta whole square divided by I theta for all theta. Note that the quantity in the right hand side of the above inequality is called the Cramer Rao lower bound or CRLB for the variance of an unbiased estimator of g theta. Let us prove the above theorem. We define the scored function s, which is a function of the vector x and theta, and it is equals to del by del theta log f theta x, which is equals to 1 by f theta x del by del theta f theta x. Now expectation of s is equals to integral 1 by f theta x into del by del theta f theta x into f theta x dx, which is equals to integral del by del theta f theta x dx. Interchanging the differentiation sign and the integration sign, we get del by del theta integral f theta x dx, which is equals to 0. Now variance of s is equals to expectation of s square, which is equals to expectation del by del theta log f theta x whole square, which is equals to I theta. Now covariance between s and t is equals to expectation t into s, which is equals to integration tx into 1 by f theta x into del by del theta f theta x into f theta x dx, which is equals to del by del theta integral tx f theta x dx by interchanging the differentiation sign and the integration sign, which is equals to del by del theta expectation of tx, which in turn equals to del by del theta g theta, that is g prime theta. If rho theta t comma s is the correlation between t and s, then rho square t comma s less than equals to 1, which implies covariance square t comma s less than equals to variance of s into variance of t, which again imply variance of t is greater than equals to g prime theta whole square divided by I theta. The equality sign holds if rho theta t comma s is equals to 1, which implies that t is a linear function of s with a positive slope. That is, there exist two constants a theta and b theta with b theta greater than 0, t equals to a theta plus b theta into s with probability 1. Since expectation of s equals to 0, taking expectations, we get expectation of t equals to a theta, which implies a theta equals to g theta. Since variance of s equals to I theta, we get b theta equals to g prime theta divided by I theta. Therefore, to hold the equality in CRLB, we must have t minus g theta equals to g prime theta by I theta into del by del theta log f theta x with probability 1. We write this equation as 2. Note that if a family of distributions satisfies the Cramer Rao regularity conditions and if Tx be an unbiased estimator of an estimable and differentiable parametric function g theta such that 2 holds, then Tx is the UMVE of g theta. Now we consider the following results. Result 1. In Cramer Rao inequality, equality holds if and only if f theta x is of exponential form. Proof. We first consider the if part. Given the family is of exponential form, we can write f theta x equals to u theta into e to the power q theta into tx into vx. We can write this as e to the power log u theta plus q theta into tx plus log vx. Taking logarithm, we get log of f theta x is equals to some k theta plus q theta into tx plus hx, where k theta equals to log of u theta and hx equals to log of vx. Therefore, del by del theta log f theta x is equals to k prime theta plus q prime theta into tx. Thus we get tx minus within bracket minus k prime theta by q prime theta is equals to 1 by q prime theta into del by del theta log f theta x, and hence the equality condition for Cramer Rao lower bound is attained. Now we consider the only if part of the result. Given that the equality condition in Cramer Rao lower bound holds, we have tx equals to g theta plus g prime theta by I theta into del by del theta log f theta x. Differentiating both sides after taking logarithm, which implies del by del theta log f theta x is equals to I theta by g prime theta into Tx minus g theta. Hence, by solving the differential equation, we get f theta x equals to u theta into e to the power q theta into Tx into Vx. So, f theta x is of the exponential form. Now we consider another result, result 2. If T is a biased estimator of g theta with bias b theta such that b prime theta exists, then MAC of T is greater than equals to b prime theta plus g prime theta whole square divided by I theta plus b squared theta. Proof. Since expectation of T equals to b theta plus g theta, it follows that covariance between S and T is equals to del by del theta expectation of Tx, which is equals to b prime theta plus g prime theta. In module 2, we have already seen that MAC of T is equals to variance of T plus b squared theta. Again, by CRLB, variance of T is greater than equals to b prime theta plus g prime theta whole square divided by I theta. Hence, we get MAC of T is greater than equals to b prime theta plus g prime theta whole square divided by I theta plus b squared theta. Hence, the proof. Now, we consider some examples. Example 1. Now, we consider some examples. Example 1. Let x1, x2 up to xn be a random sample from the population f theta x equals to theta into e to the power minus theta x, where x greater than 0. Take g theta equals to 1 by theta. We are interested in finding that unbiased estimator of 1 by theta whose variance attains the CRLB. Note that del by del theta log f theta x vector is equals to n by theta minus summation over I from 1 to n xi, which is equals to n into 1 by theta minus x bar, and hence from the condition 2, x bar is the unbiased estimator of 1 by theta whose variance attains the CRLB, and thus x bar is the UMV of 1 by theta. We consider another example. Example 2. Let x1, x2 up to xn be a random sample from Poisson population with PMF fx equals to e to the power minus lambda into lambda to the power x divided by x factorial, where x equals to 0, 1, 2 up to infinity, lambda greater than 0. Let us find the lower bound for the variance of an unbiased estimator of lambda. Note that expectation del by del lambda log of fx whole square is equals to expectation x by lambda minus 1 whole square, which is in turn equals to 1 by lambda square into variance of x, which is equals to 1 by lambda. Therefore, the CRLB for the variance of an unbiased estimator of lambda is equal to lambda by n. Next, we consider another example, example 3. Let x1, x2 up to xn be a random sample from normal mu, sigma square population with mu unknown and sigma is known. Let us find the lower bound for the variance of an unbiased estimator of mu. Here, fx equals to 1 by sigma root 2 pi into e to the power minus x minus mu whole square divided by 2 sigma square. Taking logarithm on both sides and differentiating with respect to mu, we get del by del mu log of fx is equals to minus 2 into x minus mu divided by 2 sigma square into minus 1, which is equals to x minus mu divided by sigma square. Hence, expectation del by del mu log fx whole square is equals to variance of x divided by sigma square, which is equals to variance of x divided by sigma to the power 4, which is equals to 1 by sigma square. Therefore, the lower bound for the variance of an unbiased estimator of mu is equals to sigma square by n. Now we consider some remarks on CRLB. The first remark is, if the regularity conditions are violated, then the variance of the UMVUE may be less than the Cramer Rao lower bound. Consider the following example. Let x1, x2 up to xn be a random sample from rectangular 0 theta population. We know that x ordered n, which is the largest order statistic, is a complete sufficient statistic for theta. The density for x ordered n is given by f x ordered n equals to n into x ordered n whole to the power n minus 1 divided by theta to the power n, if 0 less than x ordered n less than theta equals to 0 otherwise. By Lemon-Sheffey theorem, a function of x ordered n, which is an unbiased estimator of theta, is the UMVUE of theta. Now, expectation of x ordered n is equals to n theta by n plus 1 and expectation x ordered n square is equals to n theta square by n plus 2. Therefore, variance of x ordered n is equals to n into theta square divided by n plus 1 whole square into n plus 2. Now, by Lemon-Sheffey theorem, capital T equals to n plus 1 divided by n into x ordered n is the UMVUE of theta. Therefore, variance of T is equals to theta square divided by n into n plus 2. Now, the joint PDF of the vector x, which is equals to x1, x2 up to xn, is given by f theta x equals to 1 by theta to the power n if 0 less than xi less than theta for all I from 1 to up to n equals to 0 otherwise. Therefore, expectation under theta del by del theta log f theta vector x whole square is equals to n by theta square. Therefore, the CRLB of the variance of an unbiased estimator of theta is equals to theta square by n, which is greater than the variance of the UMVUE of theta. This is so because here the support of the distribution depend on the parameter theta. Our second remark is, the variance of the UMVUE may not attain the Cramer Rao lower bound. Let us consider the following example. Let x1, x2 up to xn be a random sample of size n from normal theta, 1 population. Suppose g theta equals to theta square. The CRLB for the variance of an unbiased estimator of theta square can be shown to be equals to 4 theta square divided by n. Now, by Lemon-Sheffey theorem, capital T equals to x bar square minus 1 by n is the UMVUE of theta square, and variance of T can be shown to be equals to 4 theta square by n plus 2 by n square. So, variance of the UMVUE may not attain the CRLB. In the present lecture, we have seen that the Cramer Rao lower bound plays a very important role in determination of uniformly minimum variance unbiased estimators. Two important facts that we have observed in this lecture are that if the regularity conditions are violated, then the variance of the uniformly minimum variance unbiased estimator may be less than the CRLB, and the another fact is that the variance of the UMVUE may not attain the Cramer Rao lower bound.